So port I/O pertains to, I'm even going to do this. I'm going to like act like there's people out there. Or I should say, hello, internets. Port I/O pertains to talking to devices. So specifically, it's doing, it's input and output to specific devices over specific ports. Different ports on the x86 hardware can be mapped to different devices. And they're kind of like hard-coded in. So it says, this port, when you talk over this port, it's always going to this device. And so a port can be input or output. So you can get data in from a device or you can get data out from it. You can write data in or you can read data out. And so, yeah, like it says, ports are created by system hardware and circuitry that decodes control and data access to specific devices. All right, so there are 2 to the 16 8-bit I/O ports numbered 0 through FFFF. And if you need to access something other than an 8-bit port, you need to take 2 ports, 2 addresses. So you could say like address 0 and 1, and you could combine them to have a 16-bit port. Or you could take 0, 1, 2, and 3, and you could combine them to have a 32-bit port. But keep in mind, you always want to do these on addresses that are aligned with the data size. So you don't want to have a 16-bit port or 32-bit port that starts with port 1 and goes 1, 2, 3, 4. It has to be 0 through, 3, 4 through 7, etc. All right, so when you access the ports, let's see, didn't put stars there, but when you access the ports, you use the in or out instructions. And in and out instructions have privilege level access checks on them. So specifically in the eFlags register, there is an I/O privilege level field which can be set, and that'll say there's 2 bits for I/O privilege level in eFlags, and this says if IOPL equals 0, then only ring 0 code can access the in and out instructions. But theoretically, kernel could say I want all of the user space code to access in and out, and it would set IOPL equal to 3, and then user space code would be able to access it. So it's again one of those. You can only use these in or out instructions if the current privilege level is less than or equal to the I/O privilege level. And so in terms of things we've actually seen before which check the IOPL, that STI for set the instruction flag and clear the instruction flag, the STI and CLI instructions, each of them actually does check if the CPL is less than or equal to the IOPL. And most OSs obviously set IOPL equal to 0 so that you don't have user space code reading and writing from devices and screwing things up. But as one could, the reason why you can think of there being, why is it not just lockdown that only ring 0 can access hardware? It's because if you think back to, for instance, that paravirtualized Zen example of picturing those rings, Zen may want to say, hey, the OS can still access something. Or if the OS was fully taking advantage of ring 1 or 2, it may say, okay, ring 1 may not, but ring 2 may not, but maybe ring 1 is allowed to still access stuff. And it may want to set IOPL so that things other than ring 0 could access it. So these are the 2 forms of the in instruction. This is a new instruction. We don't have the little star here, but this is a new one. So the 2 forms are you can take and read in from an immediate 8 to AL. So this means AL, A-low, which is an 8-bit register. It's saying read in one 8-bit thing to my 8-bit register AL. And specifically, the port address is specified by that immediate. So it would be like in AL2, and that would say read 1 byte in from port 2. Same thing if you're doing, 4 bits, you'd say in EAX2, but you'd actually be reading in 4 bits rather than 2. And again, we've got 2 different forms, an 8-bit form and the 16/32-bit form. And I said before, 16/32 is primarily determined by what type of segment you're currently in for the code segment, but it can be overridden with segment prefix, with operand size prefixes and stuff like that, which is later in these slides, and you'll have to look at it yourself because we're not going to have enough time for it. So anyways, these 2 main forms, really the only difference is This immediate one, you can specify, input-output ports between 0 and 255 because this is an immediate byte. But if you want to access all of your 2 to the 16 ports, you need to use the DX form. And so DX is the lower 16 bits of the EDX register. And therefore, the DX can hold the port that you want to access up to, FFFFF. FFFF. And so this is why actually when we had in the intro x86 class, we talked about conventions for registers, but that most of them are not, we're not actually seeing in the intro class. It turns out EDX we had said was the data I/O port. Yes, that's right. No one's here, but I'm still going. Maybe some people in there. Close that door though. Thank you. What? Thanks. So we had said that the EDX register by convention was the I/O register or something like that, and we never saw that until now. It only pertains to the in instructions and the out instructions, but this is where you actually see the convention that D is EDX, or DX really, is being used for port I/O. Out is just the exact same thing in the opposite order, so you're saying I want to output whatever data is in AL over port specified by the immediate or port specified by the DX. All right, so here's where we would do the lab parlor trick for VMware backdoor I/O. It turns out that VMware, if you go to that link, you'll see that when you have all of those capabilities that the VMware Tools gives you, the reason why you have to install VMware Tools is because actually the hypervisor is exporting this quote backdoor port so that there can be communications in and out of the VM on this using this port I/O. And so the reason you install stuff and the reason you get a kernel module installed from the VMware Tools is because the kernel, the module has to be in the kernel space in order to use the input and output to speak from the hypervisor over the port I/O, and the hypervisor catches this port I/O, and then it uses different commands and stuff, and it has fixed commands. So I'm going to quickly just show the code so you get a sense of what that port I/O looks like. But in reality, since this link is actually old and for older versions of VMware, VMware has implemented much more robust sort of RPC style communications input and output. It still works over the port I/O, but it's not as simple as this link would have you believe. This link would say, like, if you set this command, you get a copy of, the clipboard, right? So that's how copy and paste into and out of the VM works. But in reality, for newer versions, it doesn't work quite that simple. I had this demo which was supposed to just pop up a window, but it looks to me like in VMware Player, as opposed to VMware Server, which I tested it on last year, it doesn't actually work. So anyways, I'm going to set my debugger to go ahead and run so that I can get into this VM, and I'm going to break and just shut down whatever I was doing. And so originally I wanted the parlor trick thing to actually be like a full copy and paste sort of thing, and that would be awesomer because you could pretend like malware inside your VM could keep stealing your clipboard, which it can. But anyways, so the basics, this is really the core crux of it. It's just these 4 sort of instructions. First of all, you set EAX to a, quote, magic number, and this is something that the hypervisor looks for every time an in or out instruction happens. Actually, probably, yeah, an in or out instruction. So magic number goes in EAX. CX gets a command which is being sent, which you're saying is being sent out of the VM. And so in this case, this hex 12 is supposed to be popping up a OS not found dialog. I don't think it's going to work, but we'll try it anyways. And finally, there's a specific port which they use, 5658. And when you do port I/O to 5658, and you're reading the information in on EAX, and if EAX was already set to this magic number, then the hypervisor is going to expect that this is some special VMware API sort of thing to talk in and out, and it's going to do whatever you asked for per the command. So the commands could be like copy files and stuff like that. Well, maybe not copy files, but certainly copy and paste. And I don't remember the rest. You'll have to check the link. So I'm going to just set a breakpoint at the end here. Oh, wait, this was a kernel driver, so no breakpoints needed. We'll see if it actually works. I'm just going to open up my checked build environment, X, cd parlor trick, and I'm going to build-c, and then I'm going to load. Oh, there we go. Hey, it worked kind of on this one. So this little window down here, it says Windows XP is not installed on this virtual machine, but it clearly is. So really, I just succeeded in sending a command to the hypervisor to tell the hypervisor to do something. And in this case, it was just popping up like, hey, your OS isn't installed. Like, you're trying to install the wrong thing. So that was a simple example of port I/O, but it's not real port I/O because we're obviously not talking to a real hardware device. That was virtual port I/O, which happens to be relevant for understanding how VMware, at least, implements communication into and out of the virtualization system. So now we're going to do a quick example of real I/O. For those of you paying attention at home, this one you will want to do. It's kind of fun, but it will not be particularly visible what's going on unless you do it yourself. So let's see. So the next thing we want to talk about is this is an actual real thing you can do with port I/O, except in reality, since none of your PCs nowadays have a PS2 keyboard or mouse anymore, this is not going to work on your USB things. This works inside of our VM, though, because our VM exports a virtual 8042 type of keyboard controller. So way back in the day when the IBM PC was first starting out, they had a specific chip, the 8042 chip, which handled keyboard controlling. And this was hard-coded to a specific I/O line. And so if you do port I/O, you're talking to this 8042 chip, and you can send it commands, and you can pull up this PS2 keyboard link to find what commands you can send in, how you can read keystrokes out. So you will get interrupts, and then in the interrupt handler, the fact that you just got an interrupt from the keyboard controller, that's a hint to you to, hey, you should go read a keystroke out of the keyboard controller right now. And so basically, the status/command thing is hard-coded to I/O port hex 60. And the data register is mapped to I/O port 64. So if you want to send commands or check the status of the keyboard controller, you talk on port 60. And if you want to get data in from the keyboard controller, or even send data out to it, which is an interesting case, then you use 64. So the first thing we're going to do is spooky action at a distance. This is just some proof of concept code from Greg Hoglin's demo code from rootkit.com, which you probably can't get anymore. That's why I'm glad I went and grabbed a bunch of the files off rootkit.com the other day, slightly before they got hacked. So now I have most of the stuff. But this is in the rest of your code anyways. So the spooky action at a distance, all it's going to do is it's going to talk out to the keyboard controller and set some specific bits in order to enable or disable the LEDs for your scroll lock, num lock, and caps lock. So for those of you playing along at home, we want to go into the VM, and I'll do just the briefest of, I'm literally, since I'm totally out of time and I don't want to miss my flight, I'm not going to even look at the code. In the VM, you can look at the code on your own time. In the VM, we're going to change to spooky, basic hardware. Yeah, it's basic hardware. All right, so we're changing to basic hardware directory. We do build.c, shouldn't really be necessary, but we built it, and then we load it. It's going to load up the kernel module, and then it's going to start talking to this virtual 8042 keyboard controller. And if you load that up like that and you stare down at your keyboard now, what you should be seeing is that the lights are blinking on and off for the caps lock, num lock, etc. If your keyboard is like mine, the lights are not in the same order as they are bits in the keyboard controller. So the keyboard controller is going 000, 000, 001, 00, or 010. Right, so it's just incrementing up through the possible 7 combinations. When you look down at your keyboard, it's not going to look like it's moving through the binary combinations because your keyboard lights are probably not in the same order as they are in the keyboard controller. So there's that. And if you mouse outside of the VM, all of a sudden it all stops because no longer is this virtual hardware talking back to your real hardware. So you mouse in and it starts, you mouse out and it stops because it's no longer, your keyboard is no longer under the control of the virtualization system, and therefore no longer under the control of the kernel module. So you can also then stop this by doing unload, and that will stop this kernel module, and the lights will be set however they're set. So that's how you can, if you look at that code, you'll see an example of talking to the specific device. And as with any of this port I/O, you would have to know how to speak the relevant control and status reading information for that given chip. But there's going to be a spec out there somewhere that says how you talk to this chip over port I/O. Final thing we want to do is a keystroke logger using the exact same concept. But basically, instead of like setting command bits to turn on and turn off lights, it's going to get the interrupt. It's going to, first of all, hook the interrupt so that when a keyboard interrupt occurs, this malicious code will handle that interrupt. It will go out. It will speak to the device. It will get a copy of the keystroke. It will put the keystroke in its buffer. And keystrokes are not actually stored like A, B, C, D. They're called scan codes. And scan codes are really more like coordinates on a keyboard. So different keyboards with different number of keys, scan codes can map to different things. So in order for the keystroke logger to actually interpret the keystrokes or interpret the scan codes, it must have a mapping of these scan codes go to these keys. Like this is shift, this is A, that sort of thing. But we'll see the basics of this by going cd .. and bhwin keysniff. I assume this is from tutorial code from Black Hat Windows rootkit class a long time ago. So we do that. We build -c, hit return, and we load it up. And now I'm not going to push any keystrokes in there. I'm just going to mouse out quick. And I'm going to go to WinDebug. When I go to WinDebug, first of all, we see like there actually was already a bunch of, okay, these are from before. These were from the setting lights and stuff. This right here is hooking interrupt. Old address for ISR is this. New address is that. It's saying I'm hooking the interrupt for the keyboard controller. I had to specify in the code which specific interrupt it needs to hook. And now it says interrupt complete. Now when I press a keystroke inside the VM, it's going to print out the information as well as store it to a buffer for the scan code which I have typed. So I'm going to be in here. I'm going to hit lowercase a, right? And then I go outside, go back to the debugger, and it says, okay, it looks like it got scan code 1E. So to sort of justify my notion that scan codes are like coordinates, I'm going to hypothesize that if I click S, if I type S, which is, 1 horizontal from A, it should be scan code 1F because the scan codes go horizontally across the keyboard. All right, so A, S, go back to the debugger, and it says, indeed, I got 1F. And so then other things are just about, whether you press the key or you release the key and stuff like that. But basically, by understanding how to speak with port I/O, this interrupt handler that's malicious can go out and do the same thing as a normal interrupt handler would do by reading and writing to the keyboard controller. First, it reads off a copy, stores that copy, and then it actually writes back the copy and ignores the next breakpoint so that the regular hardware gets a copy of it. Because otherwise, if it just read the copy off the keyboard controller and didn't put it back, then the OS would not see any. Then OS would not be able to consume any things when it passed control to the original interrupt handler. So that is all I've got for port I/O. Maybe Corey at some point will give me some cooler examples, or at least give me some memory mapped I/O examples. So going back to the slides, I think I'm going to tear down at this point. I guess the only one thing I want to say at this point is, remember that we said you can use hardware breakpoints on input-output access. There's like a proof of concept, where is it? Did I put it in here? Yeah. Back on rootkit.com, there was a proof of concept keyboard sniffer which did not hook the interrupt controller, and instead it put an interrupt on every single access to the keyboard controller. And in that way, the interrupt descriptor table was fine, but by setting these hardware breakpoints, the malicious code would always hear when you're trying to talk to port 60. So that's another way you can make a keyboard handler. It's just a little more fragile because if someone overwrites your breakpoint handler, your thing is now blind. So what I normally would have covered is the actual detailed description of how the Intel format is set up with these prefixes I've mentioned multiple times, opcodes, how the RM32, which I've called throughout my classes, which is not really the RM32, it is actually 2 bytes, possibly 2 bytes, all right, it says if required, it is possibly an RM, it's called a mod RM, and a SIB byte, and so there may be one of these, there may be 2 of these, and then there's other stuff like displacement and immediates. But unfortunately, I just wanted to describe the early stuff in such detail that I don't have time. These are the fun things you get to go look at if you want to disassemble using your mind. All right, and the only thing I was going to say here with this content was, look, we had those examples where the opcode is listed as the same thing. So how does it know whether it's trying to do, well, actually that's not an example of what I was talking about. Never mind. So if I can quickly go over the prefixes, there's sort of 4 groups of prefixes. The first group includes things like lock. Lock will basically lock down the memory bus. So if you tack an F0 on the front of an instruction like this, lock exchange EAX with memory at EBX, right? So take the memory at EBX, put whatever's in EAX in, take the memory at EBX, put that into EAX. So switch them around with an exchange, but simultaneously lock this down so that no one else can access the memory bus at the same time, so that you can essentially have mutual exclusion. This is the only code accessing memory, so you can try to avoid race conditions. This lock prefix is the underlying mechanism by which mutual exclusion gets built up in operating systems. Rep prefix we've seen multiple times. It actually can be tacked onto a few different instructions, right? We have rep move s, rep stos, everything like that. There's actually different ways to do rep. You don't have to do just repeat until, you know, ECX is equal to 0. You can have other termination conditions like repeat and terminate when 0 flag equals 0 or 0 flag equals 1, and or, you know, ECX is 0, something like that. So there's different forms of repeat, and really there is a, right, so we said this is a move s, this is a move s D word, and that there is a separate instruction move s, and it's just A5. But you only ever see it as rep move s, and when you look at that, it turns out you've just tacked on a prefix onto an existing instruction, but there's only so many instructions you can do that on. Finally, well, almost finally, these are the segment override prefixes. You can set specific bytes in front of instructions to override things. So here's a regular jump to the memory stored at ESP. It would be FF2424. And if I tack on a 65, I look up here, it says 65 means treat this as GS relative so that we have an actual full thing. All right, so that's all. This is what we saw in this class, right? This is not so bad now. We literally covered everything in here except this XCR0, which I don't even know what that is. We also covered all of the segmentation. Segmentation goes to linear addresses. Linear addresses go through page tables to get you to a physical address. 4 fruity flavors of ways to translate those linear addresses to virtual addresses. These are the 32-bit ways, and in reality, you can only ever get to these 2 to the 20 pages, or, you know, up to this many pages. But so 1,000 pages if they're 4 megabyte chunks, or 2,000 pages if they're 2 megabyte chunks, right? But really, you only ever have access to, if you're 32-bit linear address space, you really only have access to 32 bits of physical memory at a time. All right, some new instructions we learned, more instructions we learned. And here I would normally pontificate, but you can read these just fine.